we go. All right, so today we will talk about, just a reminder of radians. Okay. How many of you are in either physics or AP physics right now? Okay, quite a bunch. Okay. Just a heads up, physics and AP physics almost exclusively use degrees, and then we exclusively use radians. So you're going to have to change your calculator back and forth all the time. So you may be like, why am I getting these numbers wrong? And then you realize you were in degree mode instead of radian mode, or vice versa. In physics, you might feel like you're getting a bunch of answers wrong, and it could be because you're still in radian mode for math. So just be aware that you do have to switch back and forth. A sinusoid. Okay, a sinusoid is not like your sinuses, not like your nose. Okay, that's your sinus. Sinusoid is a graph that follows a pattern repeatedly over and over again. Something that can be modeled by some kind of periodic behavior where you can predict the high, you can predict the low, it's going to happen over and over. All right, and then we're going to talk about transformations, how to slide those things left, how to slide them right, how to move them up, how to move them down, what happens when reflecting. So the rules of reflections are still the same as they were last time. All right, so let's jump on in. Okay, from here on out, you have to assume that everything is given to you as a radian. If it says that the angle is 2, it means 2 radians, not 2 degrees. The only time they will want you to use degrees is if they physically put the little 2 in it. So there is a difference between theta being equal to 2 and theta being equal to 2 degrees. Those are 2 different things. Okay, 2 as a radian is like 110 degrees, so it's a lot bigger than just 2 degrees. So if it doesn't have a degree symbol, it is a radian. If you want to be able to convert, some of them you should be able to convert mental math really fast. Okay, so you should be able to convert pi thirds. You should know pi thirds, okay, that's 60 degrees. You should be able to do pi. Pi is how many? 180. 2 pi, 360. Pi fourths? Okay. Pi halves? 90. All right, so some of them you should know. Some of them you will need to convert. Okay. All right, a radian is a ratio of the section of the exterior circumference of a circle. That's what a radian is. It measures how much of that out of the entirety of 2 pi, how much of that is present. That's what a radian measures. It gives it to you as a proportion relative to, instead of 360 degrees, but relative to 2 pi.
How many radians is
2 pi is the radian.
Oh, yeah.
How many degrees is 2 pi?
I'm sure.
360 degrees is 2 pi, but 2 pi is a radian. Yeah. All right. All of our radians are going to start, that's okay, with 0. Okay, 0 is on the x-axis. We start with 0 there, and we go up and around in a clockwise motion. A terminal ray, so the initial ray is always on the x-axis. The terminal ray is where you stop, always marking that, and a positive one is going to go in a counterclockwise, and then 2 pi would be 1 full rotation. That's called standard position. All right, so let's just do a couple quick things. If we want to convert from radians to degrees, use cross multiplication. Okay, don't try and memorize everything. Use cross multiplication. If you have an r over d as a proportion, then do it as pi to 180 and use it as a cross multiplication technique. So let me show you what I mean. If you need to convert pi fifths, okay, is that a degree or a radian? Okay, it's a radian because it doesn't have the symbol. So if we're going to convert that, oh, you're back already.
Yeah, I got back earlier than I thought.
Great. So you're going to put the radian in the numerator, so it'll be pi fifths above the d, that's where the r is, thanks, and then pi. So this is ratio, proportions. The radians always over the degrees. Then you cross multiply. So pi fifths times 180 equals pi d. And then we divide. So we want to divide by pi on both sides to get d by itself. So I'm going to say that d is equal to 180 pi over 5 pi. Now that can be reduced.
32.
Okay, the pi's reduce and the 180 with the 5 reduces and we get 32 degrees. Okay, so pi fifths is 32 degrees. We could also convert 2. Let's do it since we talked about 2. All right, is that a degree or a radian?
Radian.
Still a radian. Okay, it does not have 2 degrees on it. It's still a radian. So we're going to put 2 over d equals pi over 180. So we'll cross multiply that way. So we'll get pi d equals 360. So the degrees in this case would be 360 over pi. That's not reducible without your calculator. So if this is a gray problem, you would leave it like that because gray means no calculator. So just leave it as a fraction, 360 divided by pi. If you do have your calculator, you're allowed to type it in. Yeah.
Number 1, isn't it 180 divided by 5? Isn't that 36?
30. I just believed John when he said it really quick. He was so confident. Yep.
Sorry, I was thinking about this.
Good. Speak up. All right. Okay. There are some graphs that I expect everybody knows. Everybody knows what certain things look like. Let's start with a cosine. Usually people start with sine, but I'm going to start with cosine. Cosine is a graph that starts at a number 1 as a maximum. Okay, cosine is the one that starts there. Cosine then completes one full cycle. So its first full cycle going through ends up, when it ends up back at this number 1, it takes 2 pi to do that. Sine starts at the origin. Its cycle completes when you go through and you end up at 2 pi again. Okay, that would be completing one cycle. These are the normal the parent function graphs. Okay, these parent function graphs have lots of babies. Okay, they have lots of things that look similar, but they're slid either left or right or up or down, or maybe they're stretched. Okay, so maybe a parent has a taller child, maybe a parent has a shorter child. Okay, we can smush these. Tangent. I need you to know that tangent also goes through the origin, but I need you to know where its first 2 asymptotes are. Okay, it has 2 asymptotes at pi over 2 and negative pi over 2. From there, you should be able to figure out where all the rest, it's pattern. It's a periodic pattern. So you should know where the first 2 are. So in the parent function, you should get those lined up. And then you're going to need to like slide them left or right. Asymptotes can be drawn with dotted lines, or you can use like the highlighter function if you want. If you want to do your asymptotes as like yellow highlight lines, that's fine too. Okay, any questions about these? Okay, you'll see under each of them is written what the domain is. Sine and cosine are the only trig functions that have a domain of all real numbers. Okay, sine and cosine allow everything to come in. Starting with tangent, you don't have all real numbers anymore. Think about last week. What were the kind of the general guidelines for, sorry, Mr. Becker. What are some of the red flags or the guidelines for domain, Nico? Okay, if it has a denominator. So why would, yeah.
Even root.
Okay, even root, and then we also talked about logs. All right, for this one, for tangent, which of those 3 things make it so that it doesn't have a denominator of all real numbers? It has a denominator, doesn't it? what's the denominator of tangent?
Cosine.
Cosine. Okay, and so anything that's going to have a denominator cannot have all real numbers as its not domain anymore. So it would be all real numbers except all the places where cosine would be 0. So cosine would be 0 at pi halves and negative pi halves. That's why there's asymptotes there, because that's excluded out of the domain. Okay, the range is the high to low. Tangent, or sine and cosine have easy highs and lows to see. They have the low of -1 and the high of +1. Those have easy ranges. Tangent has an easy range also because its low is -infinity and its high is +infinity. So those are all real y numbers, all real y values. Okay. Or y is between -infinity to +infinity. All right, these are a little bit more of the tricky ones. And how do you remember what sine and cosine are? Here's how I remember it. Did you know that the secant graph has a cosine, an invisible cosine in it? Okay, the invisible cosine is right here. There you go. Okay, wherever, because cosine starts at 1, secant will also start at 1 because the relationship between cosine and secant are reciprocal. So what's the reciprocal of 1? The reciprocal of 1 is also 1. They have that number in common. So cosine and secant have that number 1 in common. That's how I always remember where secant goes, because I know where cosine goes. So I connect secant and cosine in my mind. I don't use it with the, it's not sine and secant. They don't both start with the letter S. It's like COS and SEC, okay? Secant is 1 over cosine. They are reciprocals. And so then I can, pick out where the high and the lows are of those different branches and the asymptotes, because the asymptotes, just like tangent, are going to line up at positive pi halves and negative pi halves. That's where they're going to go. So think about the parent function of cosine, and that will help you connect it to the secant graph. In a similar way, the parent function of sine is also part of the cosecant graph. So if you think about starting at 0, and you would create your sine graph in there. Okay, hope you can barely see that. I'll try green. Green might be a little bit better. You can just see that sine fits in there in the same way. So when sine gets to 1, that's when cosecant also is 1. When sine gets to -1, that is also when cosecant gets to -1. And then in between they have all the asymptotes. So that is another way. Okay, this domain is no longer all real numbers. It's all real numbers except all the asymptotes, because the asymptotes are where the parent function was 0. Wherever the parent function was 0, that'll create an asymptote in these. And then the range is listed twice. You have 2 ranges. You have a top range and a lower range. You have a range for the top section, and you have a range for the bottom section, so list it separately. Okay, same thing for cosine over here. You have 2 different ranges. And then cotangent is similar to tangent, except it's been a reflection and a shift. So it's reflected so that it's a decreasing function going down, but it's also bumped over because tangent went through the origin. Cotangent doesn't go through the origin. Cotangent, that spot where it used to go on the origin, has been bumped over pi halves, so it's not on the origin anymore. And it also has a decreasing. All right, we're gonna practice drawing and shifting these functions. You should remember the word amplitude. Okay, the amplitude will always be the a value in the front of a function. That determines the height. It determines the height of the sine and the cosine graph. And because sine and cosine are the parent functions, it'll also determine the values that go on the secant and the cosecant graph. We don't really worry about the amplitude for a tangent graph or a cotangent graph because those go, up forever to infinity and below. It does impact where one of the critical points are, but that's not crucial for our class. B, the B value is not the period, but it's connected to the period. It can help us figure out the period. So that value of B, now notice, we talked about this, it was Nico, it was one of the questions you had asked. B is factored out, right? Yeah? So same, you had asked about a reflection getting factored out. Same thing here, like that B has to be factored out in order to be a true B. So if you see like this, you see sine of 2x minus 4. Okay, and that is not going to be super helpful to you until you factor it out and you write sine as 2 parentheses x minus 2 like that. That's the best way to write that because the B is still fine, but it totally changes your shift sideways, your C value. All right, so we've got the horizontal and vertical shifts are done by C and D. Those behave exactly the same as last time. So if it's a positive number on a horizontal shift, it'll move to the left. If it's a negative number, it'll move to the right. And then vertical shifts just go up and down as we are used to those expected to do.
What's the amplitude in your graph?
So it depends on the graph itself. So if the amplitude on a normal graph is 1, so that tells you that we're going that the highest number is 1. If the amplitude is 3, then tell you the highest number and the lowest number is negative 3. Okay? Okay, so let's say you're given this. I would expect that you would be able to tell me the amplitude of the graph. You'd be able to tell me if it's been reflected and shifted and what its period is. So let's see if we can cover all of those things. First things first is you do want to write it in its factored form. So 4 times x plus. If I factor the 4 out, what am I left with? Pi over 4, or pi fourths. All right, so my parent function is a reflected sine graph. I know it's reflected because of the negative out in front. And it's reflected over the x-axis because the negative is outside of the function itself. I know that the amplitude is 2, which means the parent function has a high and low of 2 and negative 2. I know that the period of the parent function is 2 pi, but not of this function. Okay, the parent function has a period of 2 pi. This function has a period of 2 pi divided by 4, which means pi over 2. That means my cycle has to complete itself. I have to complete my cycle by the time I get to pi halves. So I'm scrunched together as opposed to being spread out. I have to complete that cycle by the time I get pi halves. Not like I had the luxury of getting all the way out to 2 pi. My domain is still all real numbers. You can't change the domain of a sine or cosine graph. They will always accept all values, but you can change the range. And the range has to do with the high and the low. So for this particular one, because of the amplitude, I'm going to go to the all the way down to -2 and all the way up to +2. This was just one thing about the quiz. I'll just reiterate. Range has to do with y. So if you told me your range and you used x in your range, I did take a half a point off. Okay, even if so, range is talking about the y values. All right, I think Yep, okay, so I've given you a graph on the next slide so that we can draw what we have together. So first of all, we have a reflected sine graph. So it still starts at 0, but it's been reflected to go down. So I'm gonna draw my reflection. I get my first kind of guide points in there. So it's gonna be reflected to go down. What do you wanna do? I will. I like to do my parent one first. All right, so there is one cycle. I know that my low and my high are -2 and +2. And I know in this parent function, this original thing, before I shift it, I know that the cycle has to be finished. It starts at 0, but where will my cycle end? Has to end at pi/2. So I'm going to label that pi/2. I always label after I've drawn my graph. Label it after, because then wherever you end up, you can just label it as the end, which means the middle has to be pi/4. Okay. Then I do my shift, and my shift is to the left, and it's to the left a value of pi/4. So I need to shift out to -pi/4, which is going to be right here. So then I will grab everything and move it over. So my shift will end up looking like this. Okay, so there is the cycle. Ironically, the final graph, if the original graph looked like a reflected sine, what does the final graph, the way it end up looking like? Or normal sine ends up looking like a normal sine would. Okay, so I'm going to make that bold or something so that I know what you're grading, which one to grade, or highlight it or something, so that you don't have to put both. But I find it helpful sometimes if you're struggling, you can do both. Okay, here's another one. Let's try a cosine this time. So first thing I would recommend is that you factor your cosine. So we'll have 2 cosine, and then we'll factor out the 1/2. That's going to leave me with x plus, and it's going to leave me with x plus 2 pi. How can you check your factoring work? Okay, redistribute it and just see if you end up with what you started with. So, okay, so my parent function is going to be a cosine. So I know that cosine has to start, and it's going to start with an amplitude of 2. So I'm going to draw the first part. So I do 3 dots. Okay, there's the first part of my cosine. Try not to make that too straight, because if you make it too straight, you're going to get a bunch of jagged V-like things, and this is definitely not a V. It definitely has curve to it. And then come back up and finish off your cycle. Nope, as long as your tick marks are labeled, I don't care. You'll notice I'm going to label mine now, 0, 2, and then I'm just going to label where my first cycle ended up. I don't label first, I label after. And so I want to figure out what my period is supposed to be. So I'll maybe do a little work here. My period will be 2 pi for the parent function divided by half, and 2 pi divided by half is 4 pi. So now I'll go back to my graph and I'll just make sure I've labeled the end of my graph at 4 pi. I don't have to worry about counting out to where 4 pi is. I'll just make that 4 pi. I got the power to label it where I want. Yeah.
So we just have to do that and like label, we don't have to do anything from the middle?
Yeah, so I usually do the beginning and the end, and then I'll usually do one more in the middle. Like I did last time, I said, oh, this is where pi fourths is. And I'll just say, okay, no, this is where 2 pi is. Okay, so I usually end up with beginning, end, and middle. Okay. All right, once I've got my parent function down, then I'll worry about the shift. This is another shift of negative to the left, and this is going to be shifted to negative 2 pi. So negative 2 pi is there, so I'll shift my whole graph over negative 2 pi. All right. If you look at the screen right now, I've got 5 dots, and they kind of look like they're arranged in a V. I just want to say, make sure that yours doesn't end up looking too much like a V shape. Make sure that you are making it curved as you arch from the highest down to the to the x-axis, and then curve again in that nice rounded U shape with a U. Don't make it a V. Try not to make it too harsh, and then come that. So I usually require you to do 1 cycle for me. Okay. Domain, all real numbers. Range, -2 to 2 again. Any questions so far? Okay. All right, so here's our first trig opportunity. All right, this trig is a tangent graph, but the parent function has been reflected. So my parent graph is a reflected tangent. So that will still have it go through the origin. And I'm going to put my 2 asymptotes on there. So I'm just going to do that right away for my parent function. And then get the asymptote as a reflection coming down between where the asymptotes are.
So basically like turns into a cotangent.
Almost. A cotangent doesn't go through the origin. Okay, it is have a shape of that, but a cotangent is shifted over to where the asymptote is, so it doesn't have. For a cotangent, the first asymptote goes through the origin instead of the dot. Now I'm going to label it, and I want to label it. Okay, so I know that this is positive infinity and this is negative infinity, so I've got that. But I want to label according to my period. So my period for tangent is different than sine and cosine. Its parent function has a period of 1 pi, not 2 pi. So it's 1 pi divided by 1/3. So its period is 3 pi. And what yeah.
Does that affect the cotangent?
Uh-huh, yeah, good. What I see a common mistake happen is I see students label their asymptotes as 3 pi and -3 pi, but that is incorrect. If you do that, what's the total space between the asymptotes now? It's not. All right, 6 pi, which is too large. So it's not 3 pi and -3 pi. Just divide it by 2. Just say it's 3/2 pi and -3/2 pi. Now, right. Half of it on one side and half of it on the other. Now it's 3 altogether. So you just want to make sure that you're careful about that. Nope. Okay, and then what's the last thing that's happened to this graph? Okay, shifting it up 1. Does that change the position of the asymptotes? No. Okay, does it change the range? Does it change the high value and the low value? No. Okay, so moving this up by 1 doesn't change any of those other things. Okay, still just end up here. I end up coming down in there. So there's my final graph. So you could either erase your parent function or whatever. All right, so my domain, okay, my domain is now, because tangent has a denominator, my domain is all real numbers x not equal to. There's an exception here because tangent has a denominator. And the denominator is where all the asymptotes are. So it's x not equal to plus or minus 3 pi over 2 as a pattern. But the, yeah. Yeah, okay, so then give me another example. So where the next asymptote would be after that. Okay, plus or minus, okay, another, that's gonna be plus or minus 3 pi. Because if you go out another 1.5, that's gonna be out where 3 pi is. Okay, and then on the other side. And then I usually do like dot, dot, dot to show that this just keeps going and going and going following the pattern. The range is the easy one this time. The range is negative infinity to positive infinity. Don't put the bars under because you can never touch infinity. So it's between negative infinity and positive infinity.
You put all the numbers on.
Yeah, you can put all real. Don't put all real x though, all real y.
Do you want us to like y equals all real commercial all real?
All real is fine, but don't put all real numbers x. Then I'll have to mark something wrong. Yeah, Caleb.
So if you put a line, because I'm not familiar with that notation very much, or what you did for range. So if you put a line over it, that's the equivalent of doing like a square bracket.
Right, and that would be wrong. Okay, so you would write this.
Yeah.
Okay, Jacob? Okay, all right, last one. Okay, you can see this was generated by a calculator or a computer. They want to say, from what you're seeing, can you tell what the parent function is and what the amplitude and period are? Okay, so let's say, well, what's the parent function? Can we identify that first? How do you know? Okay, it's going through the origin. All right, so let's look at this one first. Okay, I'm going to try and highlight that in red, the more, okay? Now, it's pretty easy to tell the amplitude. You can tell how high and low it's going. So for the red one, what would you say its amplitude is? Okay, 2. Now the period. You want to look at when does it complete its first cycle? Okay, when does it complete its first cycle? Well, and look at the scale. It says it's -5 to 5. So that means this is -5 and this is +5. So then this would be 4, and here would be 3, and here would be 2, and here would be 1. Okay, and then here's 0. All right, so when does this complete its first cycle? Between what two numbers? Between 1 and 2. Okay, what radian is the most common one between 1 and 2? Okay, it's close to 1.5. It's not exactly 1.5, that's close. Okay, that's pi over 2. All right, and these are meant to be good radian numbers. So its period is pi over 2. They're not trying to trick you. Okay, it's the most common number between 1 and 2. Okay, and then let's try the more softly developing one, the one that cycle is a little bit stretched out farther. Okay. All right, its amplitude, what would you say? It's 1, it's high and low. All right, its period, how long will it take it to finish its cycle? Well, did it even finish a cycle from 0 to whatever? No, but if you were to hypothesize, where do you think it would be close to finishing its cycle? Close to 6, maybe a little beyond 6, and what radian number is closest to 6? Well, what radian number is closest to 3? Well, closest to 3 is 3.14159. What number is that? Pi. Okay, so if we're closest to 6, okay, 2 pi. Again, they're not trying to make you come up with like some magic thing. They just want to know this is going to have a period of 2 pi.